In Lesson 10, we're going to review various things that we have done, some of them for a couple of years, but at least we definitely have done equations of lines since you're at least in Algebra 1, probably in pre-algebra, and rationalizing denominators and completing the squares, really something. Well, we started this in Algebra 1. I know that we did this in geometry as well. You probably did completing the square briefly in Algebra 1, but we did that a lot last year in Algebra 2. So we just want to review these three topics. So first of all, we're looking at the equation of a line. Okay, so equation of a line. So we know a couple of different forms. Okay, so one of our forms is called point slope, or let's do slope intercept first, sorry. Slope intercept form. This is probably one of our favorites. Okay, you know the form y equals mx plus b. And we call this slope intercept form because m represents the slope and b is where we get the intercept from, and particularly it is the y-intercept, not the x-intercept, it is the y-intercept. Okay, and so obviously this is used when we are given the slope and the y-intercept. So if you know those two, you can just plug in the slope for m and the y-intercept for b, and you can quickly get the slope-intercept form of a line. Okay, so that is the slope-intercept form. The next form that we use regularly is called point slope. Okay, and this really comes from the equation for slope. So let's review that. So let's look at this. So this comes from the slope equation. Okay, so the slope equation, if we want to find the slope, okay, just intuitively when we talk about the slope, we say, oh, well, that's the rise over the run. Okay, well, if we think about rise goes in the up-down direction, in the y direction. So the rise is the change in y. Okay, the mathematical way to write change in y is delta y. That delta right there means change. Okay, so delta y means the change in the y direction, or the change in y. And then the run goes this direction, the x direction. So that would be the change in x. And the way that we write the change in y, well, we would take two y values, y1 minus y2. When we subtract them, that gives us how much the y changes. The change in x is taken by subtracting two x values. And then, of course, remember that the important thing is that the x1 and y1 must come from the same point, and the x2 and y2 have to come from the same point. It doesn't matter what point you use for x1, y1, and which one you use for x2, y2, as long as you subtract them in the same order. So these two, the x1 and y2, have to come from the same point. Okay, so that equals m. Okay. So notice if I wanted to take this and clear fractions, I would multiply both sides by x1 minus x2. Okay, and on the left side I would have m times x1 minus x2, and on the right I would have y1 minus y2. And I could just change that around and have y1 minus y2 equals m times x1 minus x2 because of the symmetric property of equality. And that's usually how we think of the point slope form of a line. Okay, usually we say y minus y1 equals m times x minus x1. Okay, that's I'll write this, I'm running out of room, but we usually write it as y minus y1 equals m times x minus x1. Okay. So that's what we'll use. But it came from the slope equation. Okay. So point slope is useful used when we're given, okay, one option is if we're given obviously a point on the line and the slope. It's also used when we're given 2 points on the line. Okay. So when we'll do an example of this, but if we were given a point on the slope and we, immediately get there. If we're given 2 points, we have to do a little bit of work. So if we're given 2 points, we can use those 2 points to find the slope. And once we have the slope, okay, so using this equation, we can find the slope. And once we have the slope, we use one of the points for our x1 and y1 and then plug the slope in. Okay. And probably we should review the last form of a line, which is standard form. Okay, and that looks like ax plus by equals c. Okay. And that is often useful. We're given a word description, if it comes up usually when we're given like a real world description of a problem. It often, we write it this way and then transform it into some other form so that's easier for graphing or figuring out what the slope and what the y-intercept is, or a point on the line, etc. Okay, because this we don't know, it's not any convenient form that tells us things like points on the line or the slope of a line. Okay, the last thing we might want to review is a couple different ways that lines might look. Okay, so if we have a line that if we look at it from left to right and it's rising from left to right. Okay, so if it rises from left to right, that will have a positive slope. Okay, but if it goes and it falls from left to right, so as we're going from left to right, it's going down. So if it falls from left to right, that will have a negative slope. And then of course we have lines like this that just from left to right, they stay exactly the same. They stay even. Okay, we call this a horizontal line. And horizontal lines have zero slope. Okay. They will be parallel to the x-axis and cross the y-axis somewhere and have the form y equals some constant. Okay. This is just some constant. Okay. And then of course we have lines that look like this. Okay, those are called vertical lines. Okay, that has undefined slope, or sometimes we call it infinite slope. Okay, that will be usually parallel or on the y-axis, crosses through the x-axis, and it has the form x equals some constant. All right, so let's look at a couple of examples before moving on to the next topic. So let's say we wanted to find the equation of a line that passes through a point and is perpendicular to a given line. Notice, hopefully you recall that if we have two lines that are parallel, they'll have the same slope. Okay, and if they're perpendicular, their slopes will be opposite reciprocals. So let's write that down. So recall, parallel lines have the same slope, and perpendicular lines have slopes our opposite reciprocals. Okay, so since we're looking for our perpendicular line, we would need to find the slope of this given line and take its opposite reciprocal of that slope, and that's the slope that we want to use. Now hopefully, you know, going back to our forms, when do we use each one? Well, okay, if we are given a point on a line and a slope, which essentially we're given a point that's going to be on the line, and we aren't exactly given the slope, but we know it's perpendicular to this line, so we have a method of finding out the slope. So we're going to want to use the point slope form. But before we can do that, we need to look at this equation that's written in standard form, figure out what its slope is, and then take the opposite reciprocal. So that's the first thing we need to do. So we want to rewrite this. Okay, so we want to write it probably, and you know, y equals mx plus b. That's the easiest way to see what the slope is. So subtract 4x from both sides, and we'll get 3y equals negative 4x plus 2, and then divide everything by 3. Okay, so we would get y equals negative 4/3 x plus 2/3. So we see that this has a slope of negative 4/3, and the slope of the perpendicular then will be the opposite, so it'll be positive reciprocal, positive 3/4. Okay. So now that we have the slope that we need to use and the point, we can just do our y minus y1 equals m times x minus x1. Okay, substituting 5 for y1, substituting 3/4 for our m, and then a negative 2 for our x1. Okay, so that will become positive. So we get y minus 5 is 3/4 x plus 3/2. And then if we add 5 to both sides, we'll get y equals 3/4 x plus 5 is really 10/2. When we add 10/2, we will get 13/2. So that would be the equation of the line, that it goes through negative 2, 5 and is perpendicular to the given line. Okay. Next, let's look at this one. We want to find the equation of a line that passes through 2 points, 2 given points, 1, 0 and 0, 1. Okay, so going back to, okay, our list of used when given, if we're given 2 points on a line, we want to use point slope usually. Okay. So that probably is going to be your automatic response to this, okay, unless you realize that, wait a minute, the point 0, 1 is on the y-axis. We actually have the y-intercept. Okay, so we have 2 points. We're going to have to figure out the slope, whether we use point slope or the slope-intercept form. Okay. But this one probably would be easier for us to use slope-intercept form, because this is on the y. This gives us the y-intercept. Right. Okay. So all we really need is the slope. Okay. So let's do y1, which is 0. Minus y2, which is 1, over x1, which is 1, minus x2, which is 0. Okay, and we'll get negative 1 over 1, or just negative 1. So the slope is negative 1, and we have the y-intercept is 1. So if we plug that into y equals mx plus b, that will give the equation y equals, well, our slope is negative 1, so that's negative x. Our y-intercept is 1, so that's plus 1. Okay. Now, if we went and, used point slope form instead and plugged in one of those points, we would get the equation. It's just faster if we use slope-intercept, since we know the intercept already. Okay, so that hopefully is a good review of equations of a line. Next, let's look at rationalizing denominators. Okay, so there are a couple of different kinds of problems that we have looked at in the past for rationalizing denominators. One type is when we have irrational numbers in the denominator, like 2 minus 3 square root of 3. The square root of 3 is irrational, so we have an irrational denominator. Another example is when we have complex numbers in our denominator. Clearly, that's not a rational number. Okay, so neither of these are rational numbers in the denominator, so in both cases we would want to write these with rational denominators. So if you recall from Algebra 2, we did very similar things for both of these kinds of problems. Okay, and that is, namely, we want to multiply by 1 in a fancy form, and that fancy form is using the conjugate of the denominator over the conjugate. So conjugate over conjugate, we're really multiplying by 1. When you multiply by 1, you don't change the value of the quantity at all. Okay, so the conjugate, we just change the sign in the middle. So 2 plus 3 square root of 3. And as long as we make the numerator and the denominator exactly the same, we're really just multiplying by 1, and we're not changing the value at all. Okay, let me put some parentheses around here so we don't forget that we need to multiply this out. Now the whole reason that we do that, let's do the denominator first, is because when we FOIL this out, we'll get 2 times 2, which is 4, and then we would get plus 6 square root of 3 minus 6 square root of 3. Those go away. Okay, the middle terms drop out, and then we just have minus, and then 3 times 3 is 9. Square root of 3 times square root of 3 is 3. So that 9 times that 3 is 27. Okay. Then the numerator, we have 4 times 2 is 8. 4 times 3 square root of 3 is 12 square root of 3. Square root of 3 times 2 is 2 square root of 3. And then square root of 3 times 3 square root of 3 is 9. Okay. And so then we can simplify that. 8 plus 9 is 17. And then 12 square root of 3 plus 2 more square root of 3 is 14 square root of 3. And then 4 minus 27 is negative 23. Now, in general, we don't like to leave negatives in denominators. It's a good way to get them lost. So as mathematicians, you can write a negative out in front of a fraction. Okay, but that tends to be super dangerous because that negative can migrate up in front of the 17, and you might think it's negative 17 plus 14 square root of 3 over 23, and it's not. There's really parentheses around that, and that negative would need to be distributed to both of these. So really the best way to write this would be negative 17 minus 14 square root of 3 over a positive 23. Okay. So in general, mathematicians like to write a negative in the numerator, not in the denominator. Don't like negative denominators. They get lost way too easy in a denominator. Okay. So that's how we would rationalize the denominator when we have a square root in the denominator. Let's look at this example where we have a complex number. Well, the first thing we would want to do is write both the numerator and the denominator in standard form. So let's look at this. So let's rewrite this with 2. And then remember that I cubed, okay, is really the same thing as negative I. So we can think of this as negative I plus 2. I to the 5th is really the same thing as I to the remainder that we get when we do 5 divided by 4. The remainder when we do 5 divided by 4 is 1, so this is the same thing as I to the first, or just I. Okay, so I'll think of that as plus the denominator. If we want to put that in a plus bi form, that's going to be 4 minus 2i. So in standard form, okay, we have the real part here is 2, and then we have an I plus 2 more I, that's 3I, and then over 4 minus 2I. Okay. So that's now written in both the numerator and the denominator are in standard form, but we still don't have a rational denominator. 4 minus 2i is not a rational number. It is complex, and those are not rational. So just like we did over here, where we multiplied by conjugate over conjugate, okay, for complex numbers, we do the same thing. So we'll multiply by the conjugate of the denominator, which is 4 plus 2i, and make sure that the numerator and the denominator match. Okay. Okay, let's do the denominator first. So 4 times 4 is 16. And of course, the whole reason that we did this is because we'll get 8i minus 8i. Those drop out. And then we get minus 4i squared. Okay. And then the numerator, 2 times 4 is 8. And then we'll have a 4i. And then we'll have 12i. And then we'll get 6i squared. And then remembering that I squared is really negative 1. Okay, so this is really negative 1, and this is really negative 1. Okay, that means that we have 8 minus 6, which is 2. And then we have 16i. And here we have 16 minus negative 4, or 16 plus 4, which is 20. Okay. Okay, and since 2 and 16 and 20 are all divisible by 2, we can reduce this. Okay, 2 goes into 2 once, 2 goes into 16i 8i times, and 2 goes into 20 10 times. So that reduces to 1 plus 8i over 10. And that's the way we should write that. Okay, or you could write it as 1/10 plus 4/5 I if you wanted to as well. Okay, just separate the 10 into two different, make it like, 1/10 plus 8i over 10 and reduce it. Okay, but this is fine. That's a good way to write it. All right, the last thing that we want to review is completing the square. Okay. And so we might want to solve an equation by completing this square. So let's recall how to do that. Okay, so the first thing that you want to do, okay, is put x terms, and probably in decreasing order of degree on one side and the constant on the other. Of the equal. Okay, and we're almost there. They put the constant on the right side and they put the x terms on the left side, but they're not in decreasing order. So let's go ahead and rewrite that as 3x squared minus x equals -5. Okay, now before you can complete the square, the leading coefficient must be 1. Okay, so the second step is to ensure that the leading coefficient is 1. Okay, if the leading coefficient is 1, the rest of what we're doing will not work. This is very, very important. Okay, so since our leading coefficient is currently 3, we can't go on until we make that to a 1. So we've got to divide everything by 3. Okay, so that we have x squared, and I'm going to rewrite this as minus 1/3 x equals -5/3. And notice that I keep leaving a little bit of a gap here because eventually we're going to want to add something to both sides, so I'm just trying to give myself a little room to add something. So once we've ensured that the leading coefficient is 1, okay, and then we are going to add 1/2 the coefficient, oops, there should be an E in there, coefficient of the linear term squared to both sides. Okay, And this is really the completing the square part of it. Okay, so I need to add, what could I add right here so that this left side becomes a perfect square and I can factor it as a squared term. Okay, so if I take half of negative 1/3, I get negative 1/6. So I'm going to add on negative 1/6 squared to both sides. Okay, so I've now completed the square. So this side is now a perfect square, and I can easily factor it, especially easy if I write it in this form where I can easily see what 1/2 of the linear coefficient was. Then I know that it's going to be the square root of this, which is x. Okay, and then I put whatever's here. If it's positive, I put plus that number. If it's negative, I put minus that number, right? So this will be a minus 1/6, and that thing squared. Okay. If you write plus 1/36 here, then you're going to have to do a little bit of work to remember, you know, wait, should it be a positive or should it be a negative? So if you just write that in parentheses like that, it'll just be a little bit easier, okay, to factor, because you'll see the number that goes right there. All right, so on this side, we need to add, this one is 1/36. So let's change this number into 36. We wouldn't have to multiply this by 12 over 12. So I'm going to get negative 60 over 36. Okay, so I have x minus 1/6 squared. When I add these, I get negative 59/36. Okay. And the whole reason this is great is because now I can take the square root of both sides. And when I take the square root of the left side, I get x minus 1/6. And don't forget your plus or minus. And I need to do the square root of this. Well, we've got the square root of 59, and there's going to be an I in that because we're taking the square root of a negative number. And then the square root of 36 is 6, so that will be over 6. So that's plus or minus the square root of 59i over 6. Okay, and all right, we forgot to say take the square root of both sides. Well, first of all, factor, okay, into perfect square. And then take square root of both sides. Don't forget the plus or minus. Okay, and then finally isolate x. And we isolate x by adding 1/6 to both sides, so we'll get 1/6 plus or minus the square root of 59/6 I. Okay. And so those are our two answers. Alright, so that should hopefully be a good review of how to complete the square to solve a quadratic equation.